Okay, for this next problem, we are trying to find the current ID1 and the value of W over L. So, in order to find ID1 for part A, we first need to determine the region of operation, like we have done previously. And so, this means we need to find our VGS value to first figure out if we are in the cutoff region. Now, it is important to note about these transistors is that there is only one current going from source to ground. We'll call it ID. And that is because there's zero current going into the gates. IG is equal to 0, and that's for all MOSFET in DC. And so that means that the drain current is equal to the source current. Okay, so then, and on top of that, our NMOS mu naught COX value are the same for both transistors. Our VTH value is the same, and our W over L value is the same. And so this means that our VGS values have to be the same for both transistors. So if you look at transistor M2, we can see that the gate current is 3 volts and the source current is 0 volts. So that means that VGS has to be 3 volts, which is larger than VTH of 0.65. So we are not in the cutoff or the edge of cutoff region. Now we have to figure out what our VDS value is to see if we are in saturation. So our VDS values will also be the same for both transistors, right? Both transistors are functionally the same, so they have to have the same voltage drop across each of them. So we are trying to find the potential difference from the drain voltage of M2 to the source voltage, which is 0. So this point right here, we'll call it VDS2. One way to figure out our VDS value is by realizing that both these transistors are the same, and there's going to be the same voltage drop across each of them. And so this VDS value is going to be half of what the supply voltage is, and therefore it's 4.5 volts. And 4.5 is larger than VGS minus VTH, which is 3 minus 0.65, which means we are in the saturation region. And so, to find ID, or ID1, we use the equation 1 over 2 mu n COX W over L VGS minus VT squared. And now we just plug in our values. Our VGS is 3 volts, our VT is 0.65 volts, our W over L is 7 over 2, and our mu n COX is 0.11 milliamps per volt squared. Okay, let's see what that is equal to. 3 minus 0.65 squared times 7 over 2 times 0.11 divided by 2. We get 1.063 milliamps. Moving on to B, and here I'll do this in a different color. B is asking us to find a new value of W over L such that transistor 2 is biased at the edge of saturation. So we're trying to find a new value of W over L for transistor 2 to make it at the edge of saturation, right? So edge of saturation is right here. So VDS is equal to VGS minus VTH. And we're going to use this saturation equation. So it is a given that VDS is equal to VGS minus VTH. And more specifically, we know that VDS2 is equal to VGS2 minus VTH. So we know that VGS2 is 3. We know that VTH is 0.65. So 3 minus 0.65 gives us our VDS value of 2.35 volts. Okay, so that is what this point voltage is right here. And so that means that the voltage drop across M1, so VDS1 is equal to 9 minus 2.35 volts, which is 6.65 volts. Okay, and then we are making the assumption that our W over L value for M1 is still 7 over 2, as that has not changed. We're trying to find the W over L value for M2. So this means that we have everything we need to solve for our current, ID1, because that is equal to 1 over 2. Our mu in COX is 0.11. Our W over L is 7 over 2. Our VDS1 is 6.65 volts minus our VTH of 0.65. And we square that. All right, 6 squared, 36, times 7 divided by 2, times 0.11 divided by 2. And we get our ID current is 6.93 milliamps. Okay, this means that the current going through M2 is 6.93 milliamps. So then we can use the same equation to solve for ID2. However, we just changed the voltage. So we know our ID1 to be 6.93 milliamps, which is equal to 1 over 2. Our mu in COX is still 0.11. However, we are trying to solve for W over L. And in this case, our VGS voltage is 3 volts, right? The voltage drop across from the gate to the source is 3 volts, minus 0.65 squared. And now you can algebraically manipulate this to solve for W over L, and that W over L is equal to, let's just divide everything over onto the other side. So you get 6.93 divided by 1 over 2 times 0.11 times 3 minus 0.65 squared. Okay, let's find out what this value is. So 3 minus 0.65 squared times 0.11 divided by 2. So let me copy that, and we'll take 6.93 divided by our previous answer, and we get 22.8157. So our W over L is equal to 22.8157. So for part C, we're finding the current ID1 just like we were in part A. However, the circuit is a little bit different. So looking at it right here, we have a M2 is a PMOS transistor, M1 is an NMOS. And so how does it change when we're dealing with a PMOS transistor? Well, there will still be just one current, ID, right here. And one thing to note is that this is our source now for the PMOS, and this is our gate. And that means that our VGS, and it's important to note that whenever we're referring to VGS, we do the absolute value of it. That is equal to 3 volts, right? Because there's a 3 volt difference between the gate and the source in this case. Okay, and then 3 volts is greater than VTH, so which is greater than VTH of negative 0.65 volts. Okay, and then one thing to note, this value is actually negative, but that's because our gate and source are flipped in this case. So there's a higher potential at the source than there is at the gate. That's why that's negative. But we get away with just comparing the absolute values of both. So 3 volts is greater than our VT, which is 0.65 volts. Okay, so we know we are not in the cutoff or the edge of cutoff region. So next, let's assume we are in the saturation region. And if our equations work out, then that means we really are in the saturation region. If it doesn't, then that means that one or both of our transistors are in the triode region. So let's take the equation ID is equal to 1 over 2 mu n COX W over L VGS minus VT squared, and this is ID1. However, our mu n COX for the PMOS transistor is 0.04 milliamps per volt squared. Our VGS for the PMOS transistor we know to be 3 volts. Our VT is 0.65, and our W over L is 7 divided by 2. So let's go ahead and calculate that real quick. So 3 minus 0.65 squared times 7 divided by 2 times our 0.04 milliamps per volt squared, and we end up with 0.387 milliamps. 0.387 milliamps. Okay, so that's our part C. Okay, and I'll do letter D in purple. So again, we're trying to find the new W over L such that transistor M2 is biased at the edge of saturation. And so what this means, again, VDS is equal to VGS minus VTH. And we know our VGS for transistor M2 is 3 and VTH is 0.65. So that means our VDS value, again, is 2.35 volts. Now this is very similar to the last problem, except the transistors are flipped. So this is VDS for M2. Our VDS of 1, right? So if the voltage drop across M2 is 2.35 volts, VDS 1 has to be 9 minus the voltage drop across the transistor, 2.35 volts, which again is 6.65 volts. Okay, let's plug this into our ID equation. So let's plug in the M1 values to solve for ID, just like we did in part B. So we know that ID is going to be equal to 1 over 2 times our mu naught COX for the NMOS transistor, M1, is 0.11, times W over L, which is 7 divided by 2, times our VGS value actually is 6.65 minus 0.65 squared. And as you can see, we actually used all of the exact same values from up here because these problems are very similar. And so we actually get our ID is just equal to 6.93 milliamps, like we did before. Okay, and then for the final step, just like how we did in part B, we have to plug in our current and solve for the new value of W over L so that M2 is biased at the edge of saturation. And so the only thing that changes in our part D for this problem is actually our mu naught COX value, which changes because we are using a PMOS transistor for M2. So it changes from 0.11 to 0.04. So let me go ahead and write that. W divided by L is equal to 6.93 divided by 1 over 2, 0.04 now, times 3 minus 0.65 squared. And let me go ahead and calculate this value. So 3 minus 0.65 squared times 0.04 divided by 2. And we're going to take 6.93 divided by that number to get 62.74. 62.74. And this concludes part D of problem 1 for the fall 2018 final exam. And this also concludes today's review session for MOSFET DC analysis circuits. Thank you for watching.